get to the definition of functions today. Okay, so this is what we end up. You see, remember we defined a Cartesian product. That's the important part. The Cartesian product is a collection of order pairs. Okay, so the order pairs is going to be a relation between two elements, two subjects. So if you collect all the order pairs together, you are going to have a product. We call it Cartesian product, A cross B. Okay, and just we work out some examples of how we're going to find the collection of the orders, just the product of the sets. We get the set A and the B, and if you want to find the A cross B first, you just decide how many elements are going to have. The set A would have 3 elements, 1, 2, 3, and this is 2 elements, so 3 times 2 would be 6. So we start writing the order pairs. We connect each member of the A to one member of the B, and then we continue. Okay, so that's going to be the collection of order pairs. And we talk about it, it's all over the places. These order pairs, we are going to use it. Now, what we are going to do next is we are going to use it in order to define relations. If two sets are given to you, sets and A and the B, a relation from A into B is just a collection of order pairs. So any subsets of A cross B is going to be called a relation. Okay, so this is what we are going to do. So we start with the definition of the relations. The relations in this course are going to be very important. In this chapter, it's just an introduction to enable us to get through the functions. But we come back to it at the end of the course, chapter 8. We have one more chapters on the property of the relations, which is going to be very important. Okay, so for the time being, just get to know it. These definitions would be repeated again when you get to the chapter 8. So what's a relation from A to B? So if you have two sets, so if A and B are going to be given to us, okay, are given sets, then a relation, you may denote it by R or anything else you like. A relation R from A, okay, from A to B, to the set B, to B is going to be just a subset, is a subset of A cross B, A times B if you like. So any subsets of A cross B or A times B is going to be a relation. Okay, so in this case, if you have a relation from A to B, A is going to be called the domain of the relation, and the B is going to be called the codomain. Okay, so in this case, so if you have this relation, okay, in this case, A is going to be the domain. A is the domain. Okay, A would be the domain. A would be domain of R, and B is going to be, okay, is called the codomain. This is going to be the codomain. The codomain of the relation, a relation R. Okay, so it's going to be, in order to have a relation, you need the pair. Okay, a pair. So if you have a collection of pairs, that would be a relation. Give you example of a relation. Suppose you have two sets. So suppose the set A is given to you. Set A, you got 2, 3, and 4. So your set A would have 3 members. And we have another set, a set B. A set B would have 2 members, 4, and 5. Okay, let's set A and the B. Then we're going to give some relations. Then the following. Okay, then the following are going to be relations. The following are relations. They're going to be relations that's going to be defined from A to B. From A to B. Remember, the relation must be a collection of order pairs. So this is it. The first one. The first one is this relation. That's a collection of order pairs. We have 2, 4. This means 2 is related to 4. Then we have 3, 4. Then we have 4, 4. You see, this is going to be a relation. It's a relation from A to B because the first members are coming from the A, okay, and the second member is coming from the B. So this is going to be a relation. And the domain of this relation is A and the codomain is B, because when they say it's a relation from A to B, these two are going to be fixed over here. Any question? Now let's see what is special about this relation. You see in this relation, everybody is related to the 4. So everybody is related to the 4. So in this case, the second component, if you like, the second coordinate or the second components are all the same. You say this is going to be the one. Can you think about the relation in everyday life with this property that the second components are going to be all the same in everyday life? You see, everybody is related to one person, if you like. Any everyday life example that you can think about it?
3 siblings with the same parent.
Yes, that's correct. Yes, these are the name of the children, and this is the parent. Yes, very good. Any more example of this type of relations in everyday life? Facebook is one of them. This second one is you. The first one are your friends. So your friends are related to you. So that's going to be a relation. Or the other one is, like what's that? A dollar store, if you like. You see, if you go to a store, everything is going to be $4. Okay, everything is going to be $4. So the second one are the same. So it's happened, and it doesn't matter. This would construct a function for us in future, and that would be a constant function because everything is 4, 4, 4, 4. So the output is 4. We'll get to that, but I just wanted to give you a hint to what you look for. So let's say the first one, get the second one. The second relation is this one. We have 2 is related to 4. Okay, 3 is related to 4. 3 is related to 4. 4 is related to 5. And then again, we have 3 related to the 5. So that's going to be another relation in this case. Again, your domain is, domain and the range are going to be the same. The domain and the codomain are going to be the same. There's going to be a range. We talk about the range when we get to the function, not for the relation. Okay, let's see what is special about this one. Any suggestion? What is special about this one? Can think about it. Any suggestion? You see 2 is related to 4, that's fine. 3 is related to the 4, 4 related to the 5. 3 again is related to the 5. So we get a situation that one member from the A is related, is related to 2 members of the B. You see in the first part, each member is related to 1 member. 2 is related to 4, nothing else. 3 is related to 4 and 4 is related to 4. But over here, if you think about it, 2 is just related to 2 would have on one friend if you like. This is going to be the one. 2 is related to 4 only. 5 is related to 4 is related to the 5 only. But in the case of the 3, you see 3 is related to 4 and 3 is related to the 5. In this case, we say that the first component, okay, the first coordinate, they share. You see, there is a common first component, if you like. There is a common first component. In a minute, you will see the definition of a function. Function is a relation. A function is a relation in which you cannot have any shading for the first component. You see the first one? The first components are all different. 2, 3, 4. This relation is going to be called a function. But the second relation, because they're sharing the first component, this cannot be a function. But in the case of the relation, there is no, okay, there is nothing to worry about. There is no restriction. It's a relation. Okay, any question? Give you another one. And we are going to use all of them in a minute for a definition of a function. In this, the target in this section is the function rather than the relation. But in future, you will see the relation too. Okay, let's have another one. Let's see what is special about this one. 2 and 4 and 3 and 5. This is again a relation. What is special about this one? Let's make it different from the others. Any suggestion for this one?
No number is repeated.
And something else. There is something which makes it different from the others. You see, you want to have a relation from A to B. Okay, so in this case, all the A's, members of the A's are covered, if you like. You see, 2 is related, 3 is related, and 4. It's the same for the next one. All the members of the A are covered in the relation. But for this one, you see, you're only covering 2 and 3. You didn't cover the 4. That's the difference between these 3 together. Again, when we get to the definition of a function, definition of a function would be, a function is going to be a relation from A to B with 2 conditions. The first condition is you must cover everything in A. This means you should have the 2, 3, and 4. Secondly, they cannot share the first component. So the difficulty for this one is you are not covering the 4. For the relation, it doesn't matter because relation is as a collection of order base. You know that A cross B would have how many members? A cross B would have, this is 3, this is 2. A cross B would have 6 members. If you pick any of those 6 members and you put them together, you have a relation. So no restriction. But in a minute, you will see, we get back to this one right away. Okay, any question? And of course, you can list all the members and you have a big relation. So A cross B would be a relation. So A cross B means you have to list all the members. You know that you're going to have 6 elements. So that would be a relation. And the other obvious one is, we call them trivial one. And the other opposite just the empty set. Empty set, because the empty set is a subset of A cross B. And every subset of A cross B considered to be a relation. Okay, any question?
Sorry, Professor. So empty set is
Yes.
basically the subset of all the sets.
That's
Every
it,
set
yes.
we know.
Yes. Yes.
Also, I have a question. If you have a set that has empty set in it, so basically it has one member.
What do you mean by a set that empty set in it?
We have bracket, empty set, bracket. So it's not just nothing. There's empty set in it. You know what I mean? I don't know
No,
if
no,
I'm,
no, no. Your sentence is not logically correct.
it's not as correct. Okay.
You cannot say that I have a set in which the empty set is inside the set. Doesn't make sense.
Okay. That
This is
makes
what
sense.
you mean. You see, this makes sense. You see?
Yeah, but we cannot put the empty set in it, right?
No, no, if you put anything else in, you can call it John by empty set. If you put anything inside this, then it's no more is an empty set.
I
You
see.
see?
Okay.
Because
Okay.
you call it empty set. So it's
Yeah.
empty. Okay, it doesn't matter. You put a car in it or so this is going to be the one. We try to avoid this type of notation. That would be better to put this one. Okay, so the empty sets, you know, it's going to be, we always consider non-empty relations, if you like, but these are around all the time, okay? Especially when you do the problems in your book, you may get it, so don't be surprised. Okay, so this is a definition of a relation. We get back to the relations. We don't want to get very much involved for the time being, because we are going to have another chapter on this. But there are some, we have to give you one special notation to get to use this notation and you work with it. And then we come back to it at the end. And there is one special example of the relation that make it a collection. It's just a special group really. And that will cover all the assignments that we have. So we have to take care of those two. And then we come back to talk about the function, okay? So any question on the relation is straightforward. A relation is a collection of order pairs. So if you say it's a relation, remember these must be order pairs inside. So the order pairs, there is no restriction. It's just your, the order pair, your first members coming from the A, the second member coming from the B. And these, the last one that we put are the trivial ones. They are around all the time. Now let's have this special notation that we needed for all the assignment of this section. So what's going to be, let's say, a relation and notation that we are going to use. And that would be useful when we get to chapter 8 because we prove some theorems over it, but not for the time being. Okay, let's see what's that special notation. See, if R is going to be a relation, okay, it's going to be a relation from A to B. That's going to be relation. Then use this expression. Then given, you see, given an order like X, comma Y in, remember this notation belongs to in A cross B. So if you have a member in A cross B, then we write, you see this member can be a member of a special relation, member of the R. So then we write, this is what we're going to do, we write X is related to Y. You see, you have to put the relation here. If the relation is R, you put the R. It's F, you put the F. So we say that X is related to the R. This means if and only if this order pair of X comma Y is in your relation. Okay, you know that you can list many order pairs of the A cross B. You may have 20 members, but some of these members can be in your relations, or some of these members may not. So if you want to identify that members, that order pairs is in your relation, these are two different notations they're going to use, especially the first one. So we say X is related to R. X is related to Y. X is related to the Y, so X and the Y is member of the group, member of the club, if you like. Okay, to get this number. So this is a notation that we're going to use. Otherwise, so if this is not going to be the case, we write X is not related to Y. Okay, and if it's going to be the case that this is where X comma Y is not in R, is not in in R. Okay, in the assignment that you are going to do for us, you are going to have this type of questions, in your book. And they list some of these terms and they ask you which of the following is going to be, true or valid. So you have to know it. What does it mean? Okay, so for example, this is a situation I'm going to have. For example, if the relation is going to be, if R is going to be a collection of 2, 4, okay, and then 3, 4, 3, 4, and 4, 4. If this is going to be the case, then it's clear that, okay, then it's clear that, you see, 2, 4 is in R, so you can say that the 2 is related to 4. So when you write 2 is related to the 4, this means the order parents, the 2 and the 4, are going to be in your relation. Or you can say that the 3 is related to 4. 3 is related to the 4, but you see, but 2 is not related to 5, for example. So make sure you understand how we're going to read these type of notations. Okay, any question? So we get back to this notation again when we get chapter 8. Now that will help us to just give you one of those 4 examples that you're going to have in your assignments, so you know how to answer those. When you want to give us the definition of give us the relation, you have 2 options. The first option is you just list the members, or the members would be listed. But sometimes they give you a formula, a relationship that you can use to generate the members of the relation, okay? So these are these 4 examples that you have in your book, your textbook, okay? So I'm going to give one of them to get to know it. Any question? So make sure to understand this notation. Now, an application of this notation is this problem. And this is one group of the very famous examples that we're going to use in the future again. So let's see what's going to be that example. This is it. Example. So we are going to have 2 sets. Suppose the set A is given to you, containing 2 elements, 1 and 2. That's set A. Okay, then we have a set B. And the set B is going to be covering, okay, B is covering 1, 2, and 3. So that's a set. And then you are going to have a relation and a relation. Okay, and a relation from A to B. Relation from A to B is defined by the following. That's the expression that you're going to see on those problems. And defined by. I'm not going to list it, but they give you the definition is given. If you pick an order pair, X, comma Y in A cross B, okay, then X is related to Y, means X and the Y are going to be in, okay, in R, if and only if X minus Y, X minus Y over 2 is an integer. This means X minus 5 must be an even number, you know that. If it's going to be even number, you can divide it by 2. If you divide it by 2, then that gives you the integer. Okay, if and only if X minus 5 over 2 is an integer. So the relation is not given to you directly. It's defined by this definition. So what they ask you to do, would like you to identify all the members. Okay, would like you to identify all members of the relation. All members of the relation relation R. You have 4 of these on your text, textbook as your assignment of this section. Okay, so we are going to try. We are going to check. The first thing to do, we can form all the members of A cross B. A got 2 elements, B got 3 elements. So A cross B would have 6 elements. So identify all the 6 and you check them. If those order pairs satisfy this condition, you drop them into the R. Otherwise, you ignore it. Okay, so this is going to be the solution. So just remind you that, note that, just for your information, A cross B has what? Has 2 times 3 equal to the 6 elements. Okay, identify all the 6 elements. So it's going to be A cross B, a collection of, remember, you pick each element in A and you connect it to all the elements in B, and then you come back and you continue, and you know that you should get 6 elements. So the first number is 1. So related 1, 1, 1, 2, 1, 3. Then you come back 2, 2, 1, 2, 2, 2, 3. Okay, so these are going to be our numbers. So start with the 1, 1, 1, 1, 2, 1, 3. That is the 1. And then the next number is 2, so we do the same thing. So it's going to be 2, 1, okay, 2, 1, 2, 2, and the 2, 3. That's it. And you have a 1, 2, 3, 4, 5, 6. Any question? Now pick the one that satisfies this condition. The difference must be, okay, the difference must be what? The difference must be divisible by 2. I'm going to try to show you, but we can try a couple of them and then list all of them. So I pick the first members. So you see, according to this definition. So I have 1, 1, 1. 1, 1 is in A cross B. Okay, so form that. So this means X is equal to the 1, Y is equal to the 1. So form the X minus Y over 2. So that gives you 1 minus 1 over 2. This is going to be 0 over 2, which is equal to the 0. And 0 is an integer. Okay, 0 is an integer. Okay, so this means this is a member of your group. So this means 1, 1 is in R so far. Any question? So you have to find the list, to check to get these numbers. I try another one, then I can list all of them. Any question? So the condition is X minus Y must be divisible by 2, must be an odd even number. So the next number is going to be 1, 2, 1, 2, A cross B. So X minus Y over 2, X, Y. X is 1, Y is 2. So that gives you 1 minus 2 over 2. So that gives you negative half. And you know that negative half is not an integer. So you forget this one because this is not going to be good for you. Okay, it's not good for you. You don't have to, but 1, 2, for example, is not in R. Okay, it's not in R because it's not going to be an integer. And then you just go on and check the other ones. Okay, you check 1 and 3, for example. 1 and 3. Then you have the X minus Y over 2. So your X is 1, Y is 3 over 2. So that gives you a negative 2 over 2, which is going to be a negative 1. So that's a good one. It's an integer. So this means 1, 3 is also in R. Okay, so far you get 2 members of the R. And you just have a look and you find out the other ones. This is not going to be because 2 minus 1 would be 1 divided by 2 is not, okay. If it's going to be on the test, just do a couple of them and then you can claim the other one. So similarly, 2 and 1 is not in R because the difference is not an even number. Okay, then 2 is a good one. 2 is good one because x minus 5 would be 0. 0 divided by 2 would be 2. Okay, so this is in R. Okay, and the 2 and 3 again is not a good one because 2 minus 3 would be 1. 1 divided by 2 is just 1/2. Okay, so this is not going to be in R. So the members of your relation, the members are, you have a 1, 1. Okay, we have the 1, 1, and we have the 2, 2, 2, 2, and we have, which was the other one? 1, 3. 1, 3. This is going to be your relations. Any question? The one that you have in your book, this is x minus 5 over 2. They give you x minus 5 over 3 or over 5. Or sometimes they say, find it so that x minus 5 to be divisible by 5. Okay, divisible by 3. These are various expressions that we're going to use. It's a very popular case, so get to know it. And we are going to use it in this section, and then we come back to it when we get to the chapter 8 for the final part of the course. Any question? So nicely identified. It's going on the test. You should go a couple of cases for us and then write this one. Or you can check all of them. That would be better to check all of them. But don't just write this one at the beginning for us. You have to show that this machine is working. Okay, show that your formula is working for a couple of times, and then that gives us the final answer. Any question? So the R is going to be a relation from A to B. What's the domain of this relation? Domain?
A.
A, very good. That's a domain. Codomain?
Is B.
Codomain is B. You see, because you are having a relation from A to B. You see, when they say A to B, the domain is A, the codomain is B. So this is the way we operate. Okay, any question? So we are done with as much as relations that we need to get through the notion of the function. Now we are ready to give you one definition of a function. Okay, so what's going to be a function? In this format, a function is a relation. A function from A to B is a relation. Is a relation with two conditions. The first condition, this relation must cover all the members of the A. So basically, this means the domain of your function is A. You see, this is different from calculus. In calculus or in algebra, you write the function first. You see, write f of x equal to the 3x plus 5. Then you determine the domain of the function. But in this definition, the domain of the function is already been determined, because when we say the function from A, so this means the domain is A. Okay, so you must cover the A. This means each member of X should be able to relate to each member of the B. And this covering must be unique. Must be unique means those first component that we talk about, there is not going to be any sharing. If you pick two order pairs of your function, they cannot share the first component. So basically, a function is a relation from A to B with the condition that each X in A is related to one and only one member in B. That's the basic one. But I'm going to write it down for you. Okay, this is the way you define a function. That's a very, very good one. The notion of the function was around for years. It takes quite a while for the mathematician to arrive at a nice definition. The modern definition of a function starts with this type of relations that we have. Then we go to the classic one, which is with the notation of the f of x that we usually use in calculus. But you need this type of interpretation of the function in computer science, because your case are mostly a finite case. Okay, you're just working with 100, okay, 10, 20 cases, not most of the time infinitely many. Okay, so this type of notation and the definitions are going to be more useful in this field. Okay, so what's going to be definition? We are going to define the function. Okay, we define the functions in terms of the relations. So we call it the functions and relations. Okay, so there you are, a relation. Okay, a relation f from, okay, from a set A to a set B. Okay, a set B is called a function. It's called a function. Okay, it's called a function if it satisfies two conditions. The first condition, okay, if every element, okay, every element of A is the first coordinate or component. The first component of an order pair. Okay, order pair of F. So this means that the function must cover the A, you see. The function, see, the function F covers all members of A. It's a difference between this definition and definition in calculus. Okay, so therefore means, you know, if you like these expressions, or I give you another interpretation, or for if you give me an X, or for, okay, for any given X in A, okay, there is, okay, there is an element Y in B such that X comma Y is in F. That's algebraic format. So basically this means these members of the A must be the first component of the element in the F, okay, in your relation. Or basically the easiest one is F should cover all the members of the A. Should cover all the members of the A. So when you list the order pairs of your relation that you want to check to see if it's going to be a function, first thing to do is just check to see if all the members of the A are in the first component. Okay, so this is going to be the first condition. The second condition is this covering must be unique. So this means X can relate, associate with only one Y. So you cannot associate the X with the Y1 and at the same time associate the X with the Y2. Because in this case, you have X and Y1 and you have X and Y2. So you're sharing the first component. No sharing, okay, that's going to be one. So the second condition is going to be a different way to write this one, is no two distinct, okay, no two distinct order pairs. Okay, order page in F, in the function, have the same first component. First component, the first, not the second one. Okay, or if you like, order pairs. Order pairs in order pairs in R or in F. Order pairs in your relation, the function, cannot. Okay, they cannot have the same first component. The same first component. Okay, that's it, component. No repetition for the first component. So F must cover all members of the A, but it must cover it uniquely. Means you just cover it once to get these numbers. Okay, any question? Again, if you want to put them nicely together, I just give you another format. Therefore, that's in brief form. The brief form would be a relation. Okay, a relation F from A to B is a function. It's going to be a function if it relates. If it relates every element relate every element of A exists in A to exactly one. Exactly one element. One element. Okay, of B. This interpretation helps us to give you the definition like the calculus that you have to get these numbers. Okay, so this is a definition of the function in terms of the relation. It was the first time was given by a German mathematician. His name is Dirichlet or Dirichlet. That's going to be one. That was his interpretation of the definition of a function. It's happened to be very useful and very precise one to get these numbers. Okay, so you just look at the given relations. That's it. You check the first components. Are all the members of the A covered by the first component? And secondly, you double check it to make sure that they are not going to be sharing the first component. All the first component must be distinct. They must be different, and that give you the function. Okay, question? Give you one example. We're going to have a kind of two different types of the examples. So the first one, the usual one, like your algebra courses. So we give you a list of the relations, and then you have to tell us if this relation is a function. If your answer is positive, okay, if it's yes, no explanation is needed. But if you say no, you have to give us a reason, remember, for the test. It's not just a yes or no. Okay, we ask you to justify your answer if you like. Okay, so we have suppose. Okay, suppose A is equal to the 4, 5, 6 is one set, and B is equal to the 5, 6, and 7. Okay, that's going to be the one. We want to determine. Okay, determine if the given relation is a function. Is a function. Okay, that's going to be right. So on the test, we may say that if not, justify. Okay. If not, justify. Okay, your answer if you like, something like this. So you have to tell us which of these two conditions are violated if you like. Okay. That you claim that it's not going to be a function. So the sets are A and the B that you see over here, 4, 5, 6, and the 5, 6, 7. So there you are. Let's check the first one. First relation is denoted by T. Okay, at T, you have the following. We have the 4, 7, 4 and 7, 5 and 5, and we have a 6 and 7. That's the first one. Okay, I group it now. I write all of them so we can compare it, then we answer it. The second one is R, a relation R, and it's given to you by 5, 5. 5, 5 is 6, 6, 6, 5, and the 4 and 5. That's the second one. And the third one. The third one, let's call it S. And the S is 5, 6. Okay, 5, 6, and the 6, 7. You know that all of them are relations because the relation is just a collection of, okay, it's going to be a collection of the order base that we're going to have. Okay. So we want to know which of these are going to be a function. Remember the function, which should have two conditions. The first condition is the function must cover all the members of the A. So 4, 5, 6 must be the first components of your order base. And the second one, no sharing. So this 4 is just related to one element in the B. So no two components can share, no two order base can share the first component. If these two conditions satisfy, the answer would be yes. Otherwise, it's going to be no. Okay. So solution. How about the first one? Yes or no?
Yes.
Yes. Very good. We check the first condition. You see, we have the 4, 5, and 6 is covered. And there is no sharing for the first component. No sharing for the first component. So those conditions satisfy. So T is a function. T is a function. And with that. Okay, that's first one. Any question? How about the second one?
No, because the 6
No.
is shared.
That's it. No, because there is a sharing. You see, the first condition is satisfied, 4, 5, 6. You see, we have the 5 and the 6 and the 4. But there is a sharing here. You see, this is it. They share the first component. So this is the way you're going to answer it. No. Or it's not a function. It's not a function. Not a function. Now the justification, you say that the 6, 6 and 6, 5. They share the first comma, have the same. Okay, have the same first component. Same first component. So there is a sharing, if you like. You see, this is the 6. 6 is related to the 6, and at the same time related to the 5. This relation must be only in one direction only. Okay, so we have the sharing. That's why it's not a function. Any question? So tell us why that's going to be the case. That's part 2. How about part 3?
No,
No.
What's wrong?
not all elements in A are covered.
That's it. 4 is not covered. 4. You see, if you are in algebra, this is a function. Okay, in your previous courses, if you like, because what they do, they determine the function first, then they determine the domain. In algebra, they said the domain of this function is 5 and 6. But in this course, the domain has already been determined. The domain must be A. Okay, so that's why, according to our source, our definition, this is not a function from A to B. You can say that it's a function, but you cannot say that it's a function from A to B. So make sure you know the difference. You have to go with the rules of this course, not. This is the case if you check any book in mathematics, calculus upward. At the beginning of that, they give you a hint in the first page of the book. They say they have to justify the definition of a function that we're going to. So of course, this is the big one. But if you check the preview or the preface of those books, they explain it for you. That when they say, if it's a function, do they mean this part or the other? But in this course, the source is the domain must be covered. So the answer is no. The answer is no, and then there you are. 4 is in A, and you cannot say that it's not going to be covered, but is not covered. Is not. Okay, it's not covered. Covered by the function S. Not covered because you cannot see it over here. Okay, so these are only the 3 cases for the functions that you are going to have. Okay, any question? Yes.
If the sets aren't the same size, is it not going to be a function?
Does
if like
size
A and
doesn't?
B?
No. Size doesn't matter.
All right.
There are some other properties that doesn't matter. No, the definition is going to be what? Size doesn't matter. No. You know that you can have something like the constant function. You can have 4, 5, 5, 5, 6, 5. That's a function. And the size, okay, you can have one. No, there are some other property of the function that the size would be matter for those, not for this one. No, not in general. Okay, any question? Now, this type of interpretation is going to be useful. It's going to be useful when we work with the so-called finite cases. The finite means you see this set would have 3 elements, so that's a finite set. And this is a 3 elements, it's a finite set. But if you want to use infinite set means all the counting numbers, if you like, all the integers. So you have infinitely many numbers, elements. So this listing property is not going to be possible in those cases. So that's why we need another type of interpretation of this formula, like the one that you do in calculus. Okay, so we are going to define the function, this definition, we change them into the mechanical form, if you like. We call it function machine. Okay, function machine. In your book, they call it function notation, but it's a function machine, really. Okay, so that's going to be the one. There are we have a great conference in mathematics. It's every 4 years. It's like the World Cup. They call it ICM, International Congress of Mathematicians. Every 4 years, it's going to be in some places. Okay, I've been to a couple of them. One of them is Berkeley. One of them was in Kyoto that I went to. One was in Stockholm. So it's a great opportunity. You see all the big names over there. So it was in one of those conferences in Paris. I think it's 1950 or 40, that they argue about the definition of a function. And the declaration of that conference was to revise the definition of a functions. So they set up a group to consider what is good to define the function for the students. They propose 4 different formats for the definition of a function. This is one of them. Function and relations. We call it the modern definition. The other one is as a machine. the one that you call it f of x. The other one is for some disciplines, we just use tables, charts, a statistic. You're just using table charts. Starbucks, it's a function. The menu of a Starbucks is a function, but there is no formula for it. You need a chart. On the font line is the name of the whatever you want, cappuccino, white mocha, etc. On the other part, we get the money. You go to Burger King, it's the same thing. So that's using the charts, the tables. And the other one was graphs. So 4 different interpretations. The good books in calculus, they give you all the 4, if you check those out. So for this course, or the way we are going to use it, this is going to be the first recommendation. The second recommendation is, if we get infinite set, it's not easy to list all the members. So what we're going to do, we're going to find a formula for these members and their relations. Okay, so this is going to be called, I call it function notation, like in your book, but it's really function and machine. So that's going to be function notation. If you like the history of the function, you just search on internet, concept of the function. You'll be surprised. You see how much money has been spent in the education to get the best definition of a function. Okay, the book call it function notation, I call it function machines. So we consider the function as a machine. Okay, function machines. So what's going to be the function machine notations? You say, remember the definition of a function is just, we get a set A, we pick one element in A, X. Okay, this X in this case, we are, okay, this X, in this case, we are going to call it, okay, that's it. We are going to call it input. So this X is going to be input of the machine. Input. We drop this input into the machine, function machine. Okay, the function should give us a, okay, so the function should give us a, should match, if you like, match this one to the case that we are going to have. Okay, could you just, who is speaking? To get this. Okay, so this is going to be the input. We drop the input into the machine. The machine should find a pair for us to match this one. Okay, the action of the machine on the X would be f of X, and this is going to be the output Y. So X would be related to the Y in this manner, if you like. Okay, so in this case, this is going to be our output. Okay, so the function is going to be a machine that relates the X to the Y. But you know that this relation, the function should find only one Y that's going to be related to the X. And that's exactly what we talk about it. We cannot shade the first component. So X must shade with the Y. It can shade only once. Okay, this type of notation that we're going to use, Y equal to the f of X, is going to be called the equation of the functions. The equation of the function, some people, they call it function. Right? It's the equation of the function. And that would be useful so that we can, we can have large sets and work with the type of ideas that you usually work in calculus. Okay, so I'm going to put it into this format. It's the same thing. So this is it. Suppose f from A to B is a function, is a given function. Given function. If this is going to be the case, then f is a machine. F relates. Okay, f relates. How we're going to relate? It depends. F is a mathematical machine. Addition, subtraction, multiplication, square root, cube root, etc. So then f relates each element x in A, okay, x in A to exactly one and only one, exactly one element that we call it f of x in B, okay, in B. So in this case, we write, okay, we write y equal to the f of x as the equation of the function, as the equation, okay, equation of the function. Okay, so the first component and the second component related by a special formula, and that give you the one. It's like when you go to, okay, to a store and you want to buy something. When you select, then you go to the cashier. The cashier would scan your item. So when they scan it, if it's going to be, if it's going to be a soda, when they scan it, the machine would bring the soda machine, the soda function, and they charge you. You see, the X was the items, they scan it, the function to give you the relation, dollars, they do that. Okay, it's happened all the time. So all the cashiers are going to be, all the cashiers are functions. That is going to be the case. If you go to the fast food restaurant, you see that, they have the picture of the Big Mac or, waffles, etc. When you ask for it, they just detach or they click that picture. When they click it, they just ask for the function. Ask for the function that we were able to, to charge you. The gas station is easier. In the gas station, you select the type of the gas that you want to have. Then the machine would bring that, okay, the type 1 and lead it, etc. or the supreme one. And then they charge you. And you will see the money, that. So it's the same thing. It's function all over the places. Okay, so now in this case, in this format that we're going to have, in this format, the sets of all inputs, the sets of all, okay, all inputs or x values is going to be the domain of the function, is the domain of the function, domain of the function. And you know that in this case, function of f, you know that, which is going to be A, because in this format, the domain is already determined for us, but we call it the domain and the output and the set of all outputs in this case going to be those y values, is going to be the range of the function. Okay, is said the range is going to be the range of the function, the range of the function. Remember, the B is the codomain because the function is a relation, but the output for the function, okay, the output may be different from the codomain. So that we are going to call it the output, or we call them the range of the function. The range of the function is a subset of the B. It can be equal to B, okay? We call it, onto function in that case. But the one that is necessary to have is that the domain must be the same as the A, okay? So this is going to be another interpretation of the function to get the domain and the range. Okay, we are going to be in using a very mild type of function. It's not like calculus that we have quite a lot, the polynomials, the radical function, the rational function. No. It just, it's kind of very easy linear function that we're going to use. And of course, there are some specific one for your case that we are going to talk about in chapter 7. But knowing that this notation, it make it useful for us to be able to give you more examples. Okay, any question? So quite a lot of example of the function in everyday life. The gas station is one of them. All the cashiers are functions. Okay, sometimes you go for shopping, for example. If you go to CVS, Starbucks, etc. If you go to the sometimes the item they scan your item, and the machine does not work, if you like, and you know that the cashier would ask for the manager. What is wrong with that function at that time? You go to Albertson, you want to buy something, but when they scan your item, the machine would sound, then the cashier would ask, the cashier would be on the phone and ask for help. So what's wrong with that function at that time?
For some reason, it hasn't been mapped to the codomain.
Not the codomain. Yeah, someone is right.
Oh, the function or the value in A hasn't been mapped or covered.
So which
I
one?
think just the input was not in the domain of the function.
That's it. Very good.
I thought that's what I just said. The element wasn't covered.
No.
Oh yeah, that's the other way to put it, I guess.
Yeah. This member is not in the domain, so you cannot cover it with anything else. Yeah. But basically, I want to say that the reason is the item is not in the domain of the function. Because so what they do, that the manager would come, they open, they bring the key, and they fix it. When they fix it, they add that item to the domain of the function. Then the machine ran again. Okay, so that would be the case for your function. And we have some others, like the one that you use in calculus. The tax function is the one. The tax is very good function, but in calculus, that the function can define by several equations, not just one equation. This is again one of those things that they didn't believe it at the beginning. You have lots of arguments to accept this fact that the function can define by several equations. You know that in calculus we call them piecewise defined function. You have to partition the domain. The tax function is one of them, because the tax function x is your income. If your income is going to be between what? Between 0 and let's say $35,000, the function will bring the 10% to tax you. But if you make more money, then you go to the next bracket, if you like. Your next bracket, the function would not going to be 10%, you get a 15%. So you're going to have several equations. So that would be a piecewise defined function. The other best one is utility bills. If you check your utility bills, they explain it to you. You see, in summer they say, oh, be careful. For the electricity, there is a bracket. If you are going to be in the bracket of 0 and what's that, 200 kilowatts, then they charge you something like 43 cents, if you like. But if you go over to the second bracket, if you consume more, then they punish you. It's going to be more expensive. So that would be, again, this type of function. We are not going to use it in this course, of course. But these are different interpretation of the function to make it interesting. The function that you're going to use, your domain is going to be discrete. And this means your domain are going to be just some numbers, 1, 2, 3, 4, 5, 6. Or eventually you may use a function on the integers or on the natural numbers only. And so you don't have the type of continuity of the calculus to be able to write a nice formula for it. Or if you write the formula, you've got to be careful about the domain. Okay, so we always read the domain in this course. Okay, I should give you an example of this format to finish this one. Okay, so we used to cover the function in very much more details, and we ignore this section. We go to chapter 7. As I told you, the content of the course at the university has recently been changed. They don't like much about to spend more time on the function. So that's why we just stick with that program. So just to remind you, this is the most that you are going to use as a function. Is going to be a function, you know that. because for each X, you just what you do is like your calculator. Okay, so this is going to be a function. And then if you want to find the f of 2, as in calculus, it's going to be 3 times 2 plus 1 is going to be 6 plus 1 equal to the 7. Okay, so if you see this type of ideas in your book, don't be surprised. You have to do it and you find the value of the function for us. Okay, just to remind you, if you have this relation, x equal to the y squared, it's a relation between x and the y, but in this case, then y is not a function. It's not a function. Depends, of course, on the domain. Function of x, just for just to remind you. What's wrong with this one? X equal to the y squared. This formula won't give you y as a function of x. What condition is missing for the function? Any suggestion?
I think because y is not written in terms of x. Is that the reason? Why?
No, the answer is
It's
yes.
it's
or no.
because
Yeah.
the x can be shared. For instance,
good.
if you had 1 squared, it'd be 1, and -1 squared is still 1. So the x would be shared.
That's it. That's correct. Yeah, you have to give us, a counter example. Yes, you are right. If you put x equal to y, there are 2 possibilities for the y. Okay, if you put x equal to y, x equal to 1, then you get a y squared equal to the 1, and in this case, y would be positive -1. So you drop the 1 into the function, so you have 1, 1, and you have 1 and -1, and they share the first components. Okay, so these two have the same, if you like, same first component. Okay, so you know that we cannot have any sharing. And you know that as in algebra, x equal to the y squared give you y equal to the positive negative radical x. So that's not going to be a function, okay? So, this is the most, just to remind you, but most of the time we have our function is the members are going to be listed, so we don't have any difficulty. Okay, I should give you one more example. Any question? Just get to know them, to the new environment, if you like, of these type of problems. Nothing complicated. You're not going to have the sine function, cosine, log, exponential, etc. No, just very, very brief one, so that we'll be able to use it in some very nice function that we use in computer science. Now, this is another example. Just want to know, make sure you know and understand what we are going to ask you to do. You have, again, a couple of them. So just check your assignment on that section. I think it's 1.1 and 1.2. There are some problems, just take care of it. So suppose X is given, is a set is A, B, C. That's the X, and Y is given as 1, 2, 3, and 4. Okay, this is going to be 2 sets. But given to you now, they are going to give you a function. Now, if a function, a function f from x into y is defined by, is going to be defined by, this is it. They give you as a set of ordered pairs. We have a comma 2, means a is related to 2. B comma 4. And we have the C comma 2. Okay, so we cover A, B, C, the domain, and there is no shading for the first component, so it's a function. They call it a function. Then they ask you the following question. So the question is going to be the first part. First part, they ask you what is find f of a, okay, f of b, and f of c, the output. Okay, that's the first part. The second part, they ask you write the domain. Write the domain and the range. The domain and the range. Range, sorry, not range at this part. The codomain. The codomain of f, and eventually they ask for the range. What is the range? What is going to be the range? Okay, what's the range of f? See, that is going to be, yeah, you have a couple of them. Just make sure you know what we are going to do. Okay, are you ready? Want to make sure that how to read this example solution. The first one. Okay, what is f of a?
It's gonna be 2.
2.
F of a would be 2. Remember, we drop the a as the input into the function. Action of the function on a is the output. So I just remind you that this is the a. You see, we drop it into the function. So the output would be f of a. F of a, which is the y, remember, which is the y. So in this case, it's going to be equal to is equal to the 2. So f of a is equal to 2. It's like the y coordinate. You see, the y coordinate is going to be 2. Okay, any question? So similarly, so now we can say that f of b is equal to 4, and f of c is equal to 2. That's the first part. Any question? The second part, what's the domain and the codomain?
Well, the domain is gonna be X.
Set. Domain is going to be X, and the codomain you see, remember, it's basically a relation. But it's going to be a relation. Remember, for the f is a relation from x to y. X is the domain, y is the codomain. Okay, as a relation, we talk about at the definition. When we talk about definition, when we write x to y, so x is the domain and the y is going to be the codomain. That's going to be the y. Any question? No, we don't usually use the codomain for the function. I just want to remind you that basically it's going to be a relation. So that's going to be the codomain. Question. What's the range of this function?
The range will be 2, a set of 2 and 4.
2 and 4, yes. The range is the output of the function. You see the output of the function? 2, 4, 2. We don't consider the repetition. So the output of this function is 2 and 4. Okay, the range is different from the codomain. The codomain is the big one that's given to you. Okay, this must be, a capital, something like, just to be consistent. This is the y. Okay, so the range is the output. So the range of the function, okay, the range of f is going to be, you write it as a set in set notation, and we have the 2 and 4 only. So that would be the, Okay, the range of the function. Okay, the range going to be the output, but the codomain is already determined right at the beginning. And that's it. This is a match we need for the definition of a function and the relation to enable us to be able to get through up to the chapter 8. Okay, this is section 1.1.1.2. There is one more section that we cover. That section is about it's a graph theory, if you like. But what we do is there is going to be a couple of more about the graphs that we do later on. So what we are going to do is we are going to do those all together. So I'm not going to cover it now, because if I cover it now, it's a couple of definitions, then I get to this is one section, I think it's a 4.5. Then at that section, we have to repeat this definition again. So that's why we are not going to cover it now. If you check your sets of assignments, you will see the assignment from this section 1.4 through the chapter 4, because this is where we need it. So we are not going to cover anything else from chapter 1. We are done with chapter 1. Our main job would be chapter 2 that we cover it next week. Chapter 2 is the alphabet of logic. Remember, we talk about it. If you want to communicate, the language that we're going to use for the communication is called propositional logic. So we're going to investigate that one quickly in chapter 2 and then chapter 3. So we should be able to do up to the chapter 2 for your next quiz. So take care of the problems from chapter 1. Okay, the numbers that are already assigned. So you're done with this, and then next week we are going to talk about the logic part. That's it. Any question? So I will post the recording again. Some of you didn't show up at the first lecture. Okay, make sure that you know, because I want to make sure that you are in this course. So if you come today, then I will see your name. Otherwise, you have to have some activity. You know that you should have something that we find out that you are in this course. So if you missed the first lecture, you didn't come, you must email me and tell me that you are in. Otherwise, you will drop, because I have 8 students on the wait list. So I'll check it again today. If you are not going to be on that list, okay, for these 2 weeks, so I have to give your seats to somebody else, okay? So I waited through the weekend, and because I post this video and then you will see it. So otherwise, let me know that you are serious and you are in this course. Otherwise, we have to drop you to give your seat to somebody else. Okay, that's it. Have a good one, and see you next week on Monday. Bye-bye.
Have a good day, Professor.
Thank you.
Thank
Have
you,
a good weekend.
Professor. Thank you.
Bye-bye.
Thank you.
Right. Bye. Thank you.
Bye-bye.